Question number 74, which is the stronger base? So we have 4 different comparisons to make. So the first comparison that we're going to try to make is HS minus versus HO minus. Okay, so the way to figure out which is the stronger base is, one, you can know the pKb's of these guys and compare and contrast, or you can compare and contrast the corresponding pKa's of the conjugate acids. So, that would mean we're talking about H2S versus H2O. And by now we've talked about pKa's, so you should know the pKa of HS is around 9, and the pKa of H2O is about 15. So of the two, which is the stronger acid? Go ahead and pause and try to figure it out. Okay, so the stronger acid is going to be the H2S. So this is going to be the stronger acid. So because this is the stronger acid, it's also going to be the weaker base. So H2S is a weaker base than H2O. So H2O is the weaker acid. And because H2O is the weaker acid, it is also the stronger base. Okay, so what we've done right now is we've compared and contrasted H2S versus H2O. So, this trend will hold the same whenever you try to jump from H2S and H2O up to HS minus and HO minus. So, because H2S is a weaker base, so must be HS minus. And so must be HO minus. So of these two, the stronger base is going to be H2O. Okay, so the stronger base is going to be H2O. Okay. All right. Second one, B, that we're going to compare is going to be CH3O, or methoxide, and we're going to compare that to methyl amide, so CH3 NH minus. Okay, so again, to figure out which is the stronger base, we could know the pKb of the methoxide or the methyl amide, or we can compare and contrast the pKa. So the first question is, do you actually know a pKa for the methoxide or the methyl amide? And the answer to that is no. You don't know a pKa for either one of these. Okay, so for particularly the methoxide, it's impossible for the methoxide to have a pKa because it has no proton to dissociate on the oxygen. The protons on the carbon are so non-acidic, they're not even worth talking about. Okay, so the way that we're going to go about it is, not comparing and contrasting, methoxide to methyl amide. We're going to compare and contrast methanol. So we're going to talk about methanol, CH3OH, okay, versus, this methyl amide, or CH3 NH2. Okay, so we do actually know pKa's for the, the methanol and for the methylamine. Okay, so those are going to be, by now, these are probably going to be burned into your memory after a week or two, but the pKa for the methanol is going to be about 15, and the pKa for the methylamine is somewhere around 40, 35, 40, somewhere in there. Okay, so of these two, we can talk about which of the two is more basic, the methanol or the methylamine. Okay, so again, remember pKa is talking about acidity. The lower that number, the more acidic something is. So between these two, the methanol is going to be the stronger acid, and the methylamine is going to be the weaker acid because it has a huge pKa, so it's going to be a weaker acid. Okay, so if the methanol is a strong acid or a stronger acid, it must therefore be a weaker base. Okay, and same thing for the methylamine, since it's the weaker acid of the two, it must therefore be the stronger base of the two. Okay, so the methylamine is the stronger base of the two. So we've drawn a direct comparison between the methanol and the methylamine. So the methanol is going to be the weaker base, and the methylamine is going to be the stronger base. If methylamine is the stronger base, then the methylamide is also the stronger base, and the methoxide is also going to be the weaker base. Okay, so of those two, the methanol, or I'm sorry, the methylamide is going to be the stronger base, this guy. Okay. All right. So third up on the list, these should probably start to get a little bit repetitive. Once you can do two, pretty much you can do all of them. They're basically the same strategy to figure out. So let's compare and contrast methanol. So we can say CH3OH for methanol, and we're going to be comparing and contrasting that to CH3O-. Okay, so we can write methanol and methoxide like this, or if we really want to be fancy and actually save some time, we can write it as MEOH. So this is an MEOH. So that Me is abbreviated to mean a methyl group or a CH3 group. Okay, so we're going to compare and contrast that to an MEO-. Okay, so that. All right, so we're going to do the exact same thing. Do we actually know a pKa for one of these or for both of these? And the answer is actually at this point, yeah, we do. We do know a pKa for the methanol. So if you look up here over in sub-question B, we said that the methanol had a pKa of about 15, so that's going to be 15 right here. Unfortunately, we don't actually know a pKa for the methoxide ion, so this is a big question mark. Okay, so at this point, it may or may not be intuitive that there is a correlation between whether something is negative or whether it's positive or whether it's neutral. In general, whenever you see a neutral compound versus a negatively charged compound, you can draw a rough generalization that the negatively charged compound is going to be more basic. But if you want to be rigorous and prove it to yourself, we can do the exact same procedure as we were doing for question A and question B. So let's think about the conjugate acid of both of these. So if we talked about the conjugate acid of methanol, that would be this methanol, but this oxygen would not have just one hydrogen, it would actually have two. Okay, so we're basically putting a proton on the oxygen, and in this case what you'd have to do is you have to think about what the actual charge on this oxygen is. So if you go back to formal charge calculation, you have to remember that oxygen has 6 valence electrons. So if we're going to do a formal charge calculation on this guy, let's say formal charge on that oxygen, it's going to be 6 minus 2 lone pairs minus 1, 2, 3 formal bonds, and that's going to equal plus 1. Okay, so at this point it's okay to have to go through this calculation, but after a couple of problems, you should be able to recognize very quickly that if oxygen has 3 bonds to it, 99.9% of the time it's going to be positively charged. So hopefully you won't have to do this calculation every single time. Okay? So now let's think about the pKa for methanol. So if you think back to the pKa values that we talked about before, we gave a pKa of hydronium, or H3O+. And if you think about the structure of H3O+ versus the methanol, there isn't any difference basically in terms of the structure of the H3O+ versus the methanol, or the the methanol with a positively charged oxygen on it. So because there's basically no difference in structure, there's going to be very little difference in pKa. So if you remember, the hydronium ion had a pKa of about -2. And so therefore, since the hydronium has a pKa of about -2, so will the positively charged methanol. Okay, so the pKa for the methanol will still be about 2, or about -2. Okay, so we've protonated the methanol to give the conjugate acid. So this is going to be the conjugate acid. It's going to be this positively charged oxygen because we've tacked on an extra hydrogen. And so then we'll have to do the same thing for this methoxide. So we'll end up adding another hydrogen onto that oxygen. And so now this oxygen has 1 extra proton, and if we complete oxygen's octet, we can do a formal charge calculation if you want, or you can recognize that this oxygen has 2 lone pairs and 2 formal bonds, formal covalent bonds, and so therefore this guy's going to be neutral. It's not going to have a charge. So then we can go straight back to thinking about the pKa of just regular methanol, which we've drawn up here. So the pKa of this methanol is going to be 15. Okay. So now let's get rid of this water. So we're just going to get rid of the water. So get rid of the water. And think about now, stronger acid, weaker acid, stronger base, weaker base. So going back to the methanol, we can start to talk about the positively charged methanol. So it has a much lower pKa than the neutral methanol. So of the two, the stronger acid is going to be the positively charged methanol, and the weaker acid is going to be the regular methanol that doesn't have a charge on it. So because this positively charged methanol is a stronger acid, it must also be the weaker base, and because this regular methanol is the weaker acid, it must also be the stronger base. Okay. So again, we are talking about this methanol right here, and this methanol with a positive charge right here. So notice what we've done is we've changed the methanol and the methoxide to something that we can talk about in terms of pKa. But we've drawn a trend that should stay the same. So this trend that we drew for the positively charged methanol and the neutral methanol, this should stay the same for this methanol versus the methoxide. Okay, so now since the methanol is going to be the stronger base of these two, the methoxide must also be the stronger base of these two. So this is going to be the stronger base right here. So stronger base right here, and this is going to be the stronger base right here, and this is going to be the stronger base right there. Okay, so this was a bit convoluted, it seems, but it's only because you have to talk it out. Once you do this a couple of times, it gets really, really easy. It becomes second nature almost. Okay, so there are a couple of little minor steps that are relatively easy. The big issue that usually comes up is people mess up one little mini step and it throws everything else off. So just make sure, when you're doing these kind of problems, you have to focus in on each individual step, make sure that they each one seems okay. Okay. Alright. So the last problem we're going to do for number 74, which is the stronger base, is part D. So again, what we're going to do is compare Cl minus versus Br minus. Okay, so the question still is, which is the stronger base? And again, you can either compare pKb to talk about strength of a base, or you can talk about pKa. Okay, so pKa for organic chemistry is the easier way to think about it. So unfortunately, we don't actually have a pKa for these, so we have to do the same thing that we've done for question A, B, and C. Okay, so all we have to do is protonate both of these acids, so HCl versus HBr. Okay, so at this point, you can go down your acids, and we figured out the pKa's for all of these acids. So this is going to be, the HCl is going to have about, -6, and the HBr is going to have, somewhere around -9, somewhere in there. So now all we have to do is talk about strong acid, weak base, strong acid, strong base, weak acid, weak base. So for between these two, HCl is going to be the weaker base, so weaker acid. So this is the weaker acid, and this is going to be the stronger acid. Okay, so then because HCl is the weaker acid, it must also therefore be the stronger base. Okay, and so since HBr is the stronger acid, it must therefore be the weaker base. Okay, so now all we have to do is compare and contrast HCl and HBr to say which one would theoretically be the weaker base and the stronger base. So the stronger base is going to be HCl, and the weaker base is going to be HBr. Okay, So since we've drawn this trend between HCl and HBr, this trend should hold for Cl minus and Br minus. Okay, so it's going to hold here, and it's going to hold here. So because HCl is going to be the stronger base, Cl minus is also going to be the stronger base. So the stronger base is going to be Cl minus. And that's that. Overall, not a difficult process. It does take some time to get used to it. But if you do enough of these problems, they'll become second nature, and they actually become quite trivial. Okay. All right, moving on to next problem 75.